get started. So it's my pleasure to introduce host this week's seminar with Bryce Gadway. Before I introduce Bryce, I just wanted to make a couple other relevant announcements. The first is to remind y'all that DAMOP invited session proposals are due soon. So if you have ideas for great talks that you'd like to see at DAMOP next year, please submit them, and I will put that link here in the chat so that you can all see these. And I will also put them on a slide I'm about to show if you would like to see them there. So and the other announcement that I wanted to make was for next week's speaker. Let me share my screen. So for next week's speaker, next Vamos's speaker, not next week. We're excited to have Sarang Gopalakrishnan talking from Penn State on a topic that we will learn about sometime in the next 2 weeks. And so November 19th, he will give the talk. So without any more delays, let me introduce Bryce. So Bryce is today's speaker, Bryce Gadway, coming from University of Illinois. Bryce is a pioneer in the study of synthetic matter, which is the topic of his discussion today. He has been at Illinois since 2014, and before that he was a postdoc at Boulder, working with Jun Yi and Debbie Jin, and before that he did his PhD at Stony Brook. He's won several awards, including the NSF Career Award and others. So without any further delay, Bryce, I'll turn it over to you. Feel free to share your screen. Okay. And how would you like us to stop you for questions?
Oh yeah, just interrupt. Just yell, just interrupt. Whatever's good. Yeah. So stop me if anything's confusing. This is a seminar, so I don't really care if I finish. I don't want to lose anyone on the way.
So I'll track the Google Docs, and probably if there's a good stopping point, maybe a third or a half, do take a pause, and I'll read any questions that have accumulated.
Okay. Yeah, we have a couple breaks along the way. So yeah, thanks a ton to the organizing committee. It's basically a list of like my favorite people in the field, so it's great to get a chance to speak here. I'll talk about engineering Hamiltonians. I'm really into sort of just the nuts and bolts of doing experiments and sort of building up new tools in the toolbox, and in particular sort of techniques based on synthetic dimensions, where you're sort of having transport in something that's not just sites of a lattice or some real space degree of freedom, but something a bit more non-standard. And so here I'm showing a couple different platforms we have in lab, and I'll try to give a little bit of an overview of what's going on in the field as well. So at the start, I'd like to kind of acknowledge the whole research team, because they're the ones who do all the work. I'm at a point now, 2014. I guess I've been here long enough where I'm not really allowed to do anything in the lab. And I've graduated the first cohort of students. So Jackson just left for ETH Zurich and Paul Scherrer Institute to work on ions. Eric's at Los Alamos now, Mike Martin. And Alex is at Honeywell Quantum Solutions. Now we've moved on to kind of a new stage of students. Here's the new team working on Rydberg synthetic lattices on a project kind of co-run by Jake Covey. With neutral atoms, BECs, we have Shraddha Agrawal, Sai Paladugu, and Simon. On a joint project with Brian DeMarco on molecules, which hopefully will bring to synthetic lattices eventually. We have Garrett Williams and Michael Hyman, a great team. And then we have an undergrad project on kind of AMO inspired technologies, currently run by Yasha Signal, and then former students Rithi and Wade now with Deep Gupta at Washington. Okay. And then a ton of theory collaborators who I'll acknowledge along the way. But that's kind of the most fun part of this kind of research, that you get to work with a lot of great theorists like Caden and others. So I'll do a quick shameless plug too for IQUIST. Like every other institution across US and Canada, we have a quantum center now. But the great thing is we do have a lot of new young quantum faculty. So Vamos community member Elizabeth Goldschmidt, Jake Covey, who I was just talking with Caden about. Both of them work on kind of AMO-like things, quantum memories and alkaline earth arrays. And then kind of solid state QIS people, Angela Koo and Wolfgang Pfaff, working on superconducting cavity QED and superconducting qubits. So if you're a grad student looking for a job, there's a lot of good experimental groups here, and hopefully quantum information theory higher this year as well. And a lot of activity outside of physics as well. Okay. So after that shameless plug, here's the outline for the talk. I'll give a little bit of an overview on synthetic lattices. It's kind of a weird buzzword. I'll try to unpack what it is. And then I'll use it in every other bullet point. So here's, I'll talk about synthetic lattices of atomic momentum states, where they constitute the sites of a synthetic lattice. I'll talk about synthetic lattices for spin systems like molecules and Rydberg atoms. And then I'll talk about a kind of neat project we have on mechanical systems and how we think about engineering transport in that system by similar techniques. Okay, so I won't spend too much time on kind of the very broad overview given the audience, but in terms of motivations for engineering Hamiltonians in artificial materials made of atoms, molecules, and light, there's sort of three major pillars I would think of. So one is just sort of fun demonstration physics, sort of exploring new phenomena and states of matter for the ideas of promoting new ideas, maybe bringing new things to life, like supersolidity, where maybe one can calculate it, but if it hasn't been brought to life in the lab before, it's worth investing here in an experimental platform. There's maybe actual things like analog quantum simulation, where you're actually getting some advantage over classical techniques, numerical calculations. And I'd say that field is sort of just starting to take off and sort of get the fruits of the labor of this community from the past few decades. And then there's things as applied as quantum metrology, where you're engineering Hamiltonians maybe of a spinor gas or some other system to basically get some entanglement that you can use for some other application, like maybe measuring some fundamental constants or trying to discover dark matter particles. So I won't try to cite all the relevant groups who've worked on these things over the past few decades, but this whole sort of enterprise of engineering Hamiltonians has been sort of built up by a couple key techniques or areas. So optical trapping, sort of dipole trapping of neutral matter, and the large expanse that comes with that in terms of designing different kinds of optical lattices for atoms. Some really powerful things like quantum gas microscopy sort of live under this framework. Control of interactions. So in atoms, one has sort of just pure magnetic Feshbach control of interactions, kind of optical dressing of interactions. And then the same thing has recently sort of been carried over to molecules as well, to use sort of dress state techniques to change the interactions between molecules. Somewhat more recently, only dating back, I guess, maybe a decade and a half, are ideas of flow K engineering. First undertaken by people like Nate Gamelke and the group of Steve Chu, and sort of making some really strong connections to condensed matter, actually, where it's sort of a state-of-the-art technique there in terms of using driven system and techniques to engineer Hamiltonians. And we have a lot of neat capabilities in cold atoms to do that as well. And then maybe not on the same level as these other three, but something kind of germane to what I'll talk about today is the suite of techniques sort of inspired by synthetic dimensions. We're using the long, kind of long lifetime internal states, long lifetime motional states of atoms to sort of to access another degree of freedom they can use to study transport. So systems that are really cold and have long-lived internal states and even external states like motional states are really relevant here. And so most of these are in AMO, but even things like superconducting qubits can admit synthetic dimensions techniques. Okay, so this is a little bit niche, but what the heck is a synthetic dimension? So I'll just motivate this maybe by the earliest paper that really started using this terminology, even though some ideas of sort of internal state analogs of transport date back well beyond this, many decades. So this paper by basically the IQFO group, Maciek Levenstein, Alessandro Celli, and coworkers on using internal states to actually access fourth dimension to study transport and sort of beyond 3D. And some work by one of our collaborators, Hannah Price, and her coworkers, and actually using this to a slightly more applied topic of studying four-dimensional quantum Hall physics with cold atoms using internal states as an extra dimension. And so I'll show this graphic from this first paper by the IQFO group, where this maybe is a bit hard to follow. You're actually trying to engineer the true connectivity of a four-dimensional system by using internal states as an extra degree of freedom. So we'll use this much simpler diagram from a follow-up work where one can consider sort of a 1D real space system, so this 1D chain of maybe real space sites of a lattice, and accessing an extra dimension to study transport, say through the internal hyperfine states of some neutral atom. Okay, so this is maybe straightforward how you access extra dimensions, and then maybe the harder question is sort of what do you get from this? So some fundamental things is that, yes, in principle, I can study four-dimensional physics, which would be hard by any other method. It turns out that just the idea of coupling internal states to study transport along an internal state dimension gives a lot of other practical advantages. So in particular, if I imagine this simple system where I just have two states, 0, and they're of this little red atom here. If they're at different energies, I'm going to couple them by driving the system in some way. Let's imagine by electromagnetic fields, either microwaves or some oscillating electric field. And this dipole-driven transition between these two states naturally gives us the ability to control the phase of the tunneling in the system. So this is different than sort of the hybridized tunneling that you get between nearby spatial states, like in a double well, where for neutral particles like atoms and molecules, the tunneling is necessarily real valued. Here, you can basically write on whatever old phase you want. When the particles move between states 0 and 1, they're going to pick up the phase of the oscillating field that's used to drive the transition. And in a proposal shortly thereafter, so Ian Spielman and coworkers showed how this could be used combined with recent techniques of sort of Raman dressing to engineer artificial gauge fields to study things like the quantum Hall effect with neutral matter. And in sort of a true testament to how powerful this proposal was, it was shortly taken up the following year by two groups, so Ian's group and the group of Leonardo Filani at Lens, and realized to study in kind of small systems, so only 3 sites in the internal dimension or 3 sites in the synthetic dimension, to study real kind of integer quantum Hall effect type dynamics. So sort of skipping edge states by one of the organizers, Szymon Kolkowicz. This was realized in kind of optical lattice clocks with long-lived electronic states, actually, in this case, and also in the group of Leonardo Filani with ytterbium, to realize a kind of spin-orbit coupling in that system where you have control over artificial gauge fields or artificial magnetic fields for neutral matter. And then in the more recent years, the group of Sylvain Nessembene has sort of taken this to the limit where you use some high spin atom like dysprosium. And here, this JZ, this is basically a proxy for the internal magnetic projection state. And with such a large spin, you can realize both edge dynamics and bulk dynamics, and they're kind of clearly disambiguated in the system. So yeah, this has been kind of the main, one of the main, in cold atoms at least, one of the main motivating reasons to study synthetic dimensions. But it's actually a much broader kind of idea that's used for quantum simulation well outside of cold atoms. So I'll ask this question again, sort of what are synthetic dimensions and what are they good for? To first answer what they're good for, they're both good for fundamental reasons. So if I really want to study something like 4-dimensional or 5-dimensional quantum Hall systems or any kind of higher dimensional systems, I really need to think a little more abstractly about how I'm doing my quantum simulation. And I think anything that any kind of approach that you're using will probably fall under the framework of synthetic dimensions. I can give you exotic interactions. I think about how real space interactions are sort of carried over to this internal space. And then some practical advantages, things like stable gauge fields without heating, some novel probes, something from work of Caden and Tom Killian at Bryce, and then access to novel geometries as well by studying transport in internal space. Okay, so now what are they? I was lucky enough in before COVID times to leave my house and go to a conference, a really nice workshop put on by Oded Zilberberg here at Zurich. And one of the topics of the conference was basically establishing what exactly is this new area of research, what falls under the framework of synthetic dimensions and what doesn't. And I think my own takeaway from this workshop was basically anything can be called synthetic dimensions if it's helpful in terms of either carrying out experiments or interpreting experiments on transport or dynamics in some new way. So that means a lot of things kind of fall into this framework, and I think that's great. So for atoms and molecules, this means things like Raman lattices or sort of internal hyperfine states of atoms coupled by lasers. Optical clock state lattices, like I showed from Shimon and Junyi, where you're coupling with laser light, long-lived ground states and excited states. Rydberg synthetic lattices and molecule synthetic lattices, where you're coupling actually with things like microwaves and RF, internal states of atoms and molecules. So here's just hopefully, unfortunately, an incomplete list probably of researchers working in these areas. Tom Killian and I believe Simon Cornish working on these dipolar systems. Because motion is long-lived and these systems are ultra-cold, you can have coherent motional states that live for a long time. So things like trap states, really just harmonic oscillator states of a trap. Momentum states, something that we study, angular momentum states. All of these can serve as sort of states or effective sites of a synthetic lattice. And I'll describe that in a bit more detail later on. And what's kind of fun about this field is you learn about entirely other platforms. So things like light or photons, where one can generate synthetic lattices out of frequency degree of freedom, some spatial mode like waveguide modes here in this work of Moti Segev and his group. And then there's a whole bunch of things that I didn't show, which is sort of reinterpreting things that people have done for some time through the framework or through the lens of synthetic dimensions. So things like dimensional extension or dimensional reduction, the idea that through embedding some parameter in a system, I can actually have access to higher dimensional physics. So there's a well-known kind of mapping between the Aubrey-Andre model for quasi-periodic lattices and the Hofstadter model for 2D lattices. And similar things exist for Thouless pumps. And actually, just a few years ago, there was a really nice set of results from both photonics in the group of Mikhail Rexman and atomic physics in the group of Emmanuel Bloch on realizing 4D quantum Hall physics in these systems. Things like time bin multiplexing, things that people here in my department use for very practical purposes like quantum memories, but it can also be used to study fun transport problems like Anderson localization, and here even realizing superfluidity of light in these sort of fiber loop systems. And then other things like quasi-periodic driving, which touch systems as disparate as kick rotors in topological pumps. And then even frequency comb systems can kind of be seen through the light of synthetic dimensions. Okay, so that's a lot. I just wanted to basically cover all the bases. And if your system wasn't covered, it's probably also described by synthetic dimensions if you think it is. At least I'm willing to say that. So my group's, one of our niches in this area is basically spectroscopic Hamiltonian engineering, which is to say that we're taking systems that have a bunch of states that would normally be mostly uncoupled unless we're applying a driving field to the system. This driving field can be sets of laser light used to drive Bragg transitions, or it can be microwaves meant to drive internal state changing transitions. But the basic idea is that the details of this drive spectrum fully determine the Hamiltonian that's going to take place in the synthetic lattice. And so it's sort of using what are some of the key characteristics of AMO systems, that we know the landscape of our internal states really well, and we have really good control over the fields that would drive transitions between them, and using that for Hamiltonian engineering. So it's a little bit different, and maybe avoid some of the hard work of doing really good optical engineering, but pushing all of that hard work onto RF and microwaves. And so the systems I'll tell you about in the rest of the talk are things like momentum state lattices and Rydberg lattices, where this kind of drive spectrum will be in the frequency distribution of some laser field or some microwave. And just to make some connection to your last VAMOS talk a couple weeks ago, these can be seen as kind of the single particle engineering, or engineering the single particle part of the Hamiltonian in a way that's comparable to what Monica does with cavity systems, and really what people have been doing with trapped ion systems in a long time, where you're driving the system with some frequency spectrum of your driving field and engineering some many-body Hamiltonian. And here we're mostly controlling the single particle part, and the interactions are just kind of coming along for the ride and hopefully enriching the system in some way. Okay, so with that, we'll have a little break, and then I'm going to switch to talking about kind of our starter platform of synthetic lattices and momentum states.
Great. So thanks for the first beautiful third of your talk. And if you have questions, please enter them in the Q&A. The chat is disabled, so enter them in the Q&A box. We have one question, really provocative question I like, from Lindsay LeBlanc, which says, all the synthetic dimension examples that you give are for a discrete variable. Is this required, or can a continuous variable be considered as a synthetic dimension?
No, this is a great question. Yeah, I think so. Everything looks simpler if it's discrete. Certainly all the internal state stuff, especially if I'm doing some frequency resolved coupling between states, it really benefits from being discrete. But for some of these cases of embedding an extra dimension through some parameter, like thallus pumping, that can really be continuous. So I think it's a very different kind of type of synthetic dimension, but that can certainly be continuous. And then, and it depends on how you want to take it. So some of our momentum state techniques, we've been thinking about applying sort of at lower energy and really tuning continuously the coupling between momentum states. And it might just be easier to interpret that as sort of low-K engineering of band structures at that point. If it's all happening kind of continuously and at lower energy, yeah.
Great. So there's another question from Eduardo Ibarra Garcia Padilla, who asks, how does this approach compare with the others you presented with respect to heating? And if I can extend that question just a little bit, you did list 10 or a couple dozen different synthetic approaches. Who needs all these approaches? Why?
Yeah, all the different approaches, they all have their own. They all come from different people working in different platforms. I think one of the nice things about synthetic dimensions approaches is that for the most part, you can just add it into your system at very much cost. So for people already working on molecules, you can just add on some microwaves. And I say that, not doing it, you have to do a bit of mapping out to get it to work. But it's less invasive than a lot of other things you would add to your system. It lives outside your vacuum system. You can add it on. I think the comparison is maybe to something like flow-K engineering. I'll try to use that as the straw man. And what I would say is it's the huge separation of energy scales. When I'm driving a transition in an atom that's, let's say 6.8 gigahertz, I don't assume that there's going to be any subsequent heating from that transition. And it really has to do with sort of the separation of internal and external energy scales. And when you're doing something like flow-K engineering of bands, you don't really have a good separation to speak of. You maybe have a ground band and excited band, separated by tens of kilohertz, and your bandwidth of this lower band is also of the order of kilohertz. And I think that's basically the crux of it. Really is it's the same kind of technique. You're doing some dressing to get some new physics, but you just start with a much larger separation of energy scales, and you don't deal with as much crap that comes out like subsequent heating.
Great. So that looks like that's it for the questions for now. So why don't you go on to the next part of your talk?
Okay. So I'll talk a little bit about this platform, which is really sort of our very textbook way of getting ourselves into this synthetic dimensions approach, where we know everything about the spectrum of our system, and we can predict really well how to drive the system to get the Hamiltonians we want. So we're starting with something that's been studied for many decades, basically just free atoms, and driving transitions between momentum states. This is one of the earliest things people did for atom interferometry, dating back way to the 80s and before. Thinking about using lasers to couple states of motion of atoms. And here we're going to start with a really cold source, so an atomic BEC. And for some things I'm going to talk about regarding interactions, this ends up being rather important. But for the most part, it's basically just meant to get a really narrow in momentum space source. So if I just put in a mirror here and send the light back and just have two counter-propagating lasers at the same frequency, what I'll find is that, yes, I can couple the different momentum states. This is a nice old result from the group of Trey Porto. But what it kind of looks like in this case is that I can couple many sets of momentum states separated by two photon recoils. But it's like they live in this potential energy landscape, which is just p squared over 2m dispersion relation of the atoms. So my atoms kind of go out, and then they get focused back in due to some interference, or basically being off resonant. And so there's some time scale associated with this. I can sort of get around this and get a lot more control if I operate in the sort of Bragg regime, where my Rabi rates are quite a bit smaller, but I've now detuned my laser to basically compensate for this difference in kinetic energy between my states. So I'm resonantly driving this transition now instead of off resonantly driving it. And I can think about this Bragg coupling between the states as basically defining the hopping element between sites 0 and 1 in my system. So I have control over the amplitude, this omega, and also the phase of this term. And if I want to extend this not just to 2 sites, but to a lattice, all I really have to do is turn on multiple tones. And I think one of the selling points of this technique is that it really is just kind of dumb easy to do. This RF engineering of lasers is really simple and ends up being quite forgiving in a lot of different respects. And through this spectrum, you can just define your Hamiltonian in a really one-to-one mapping. So all of these tones here directly relate to the tunneling terms and the site-to-site energy differences, or sort of the effective site energies of a 1D tight binding lattice in this simple case. And so there's some rotating wave approximation here, but that's it. You can kind of intuit how it's going to look. And I can turn things on suddenly and get some dynamics. And it's also quite forgiving in that I access all my states for free just by letting the atoms go. No Stern-Gerlach, they just sort of, they're momentum states, they separate. So I can take a picture, not quite with a phone, but almost. And here's a picture. Here's a movie. You just take many pictures after many different evolution times. And this is a simple case of basically starting with atoms in the middle of a lattice and watching them expand and seeing some ballistic motion. And so in this simple platform, what do you get? What do you get from this control? You certainly get gauge fields for free. So if I introduce some pathways with some closed connectivity, so something beyond just a 1D lattice, I can engineer kind of effective magnetic fields or artificial gauge fields. And I can do weird things like have inhomogeneous magnetic fields or inhomogeneous gauge fields. I can combine gauge fields with other terms like disorder or quasiperiodicity. So this is us kind of tuning through a mobility, actually turning on a gauge field in the system. And maybe less standard, are introducing things like non-Hermiticity in a cold atom system. This is through loss. And then this is a work I really like. I didn't do it. That's why I like it, I guess. That's from the group of Bo Yan at Zhejiang University, where they combine this, this non-Hermiticity, this basically loss, with some other bells and whistles to actually get non-reciprocity in a cold atom system, which seems crazy. Non-reciprocity basically means they have a different probability for tunneling to the left than to the right. It sort of defies Newton's third law, but you can get it by mixing the right ingredients in a system. And so what I would say actually is the strongest asset of the system is all this fine tuning that you get from spectroscopic Hamiltonian engineering. And in particular, kind of the studies you would do with disordered systems or quasi-periodic systems that rely on that fine control. So one thing that we studied a couple years ago now with condensed matter theorist Taylor Hughes here and Pietro Massignon from IQFO and UPC was thinking about how I combine something like band topology that I would get in this really, simple kindergarten toy model of the SSH model for band topology, how that gets enriched by adding disorder to the system. And so here we're kind of inspired by some earlier theory work by Taylor, where I can add on this W. This is some parameter characterizing disorder. This is actually off-diagonal disorder, which is a bit weird for cold atoms. Normally we think of sort of changing the landscape of potentials, but this is more leaving that landscape completely flat and instead changing the tunneling elements between sites. And here we can just dial in everything we want through the frequency spectrum of our field. So what we found is that we could measure a quantity which related to the topological index of these systems. This is something called the mean chiral displacement. Pietro cooked this up. It sort of relates to things that people studied earlier in optical systems. And it was indeed quantized for low disorder. And by really cranking on disorder here, we could destroy the topology of these bands. And if anybody's familiar with sort of the 2D variant of this, so the quantum Hall transitions, this is of the same exact type. So what you're doing is sort of successively destroying bonds in your bulk. You're creating these very large states that have low energy and bring them into resonance with the states that live at the boundary of your system. And then those states are hybridizing and basically destroying the topology of your edge states. So it's this float and annihilate type transition that happens in the quantum Hall system. And maybe what was more counterintuitive, certainly we didn't expect it when we started this whole study, was that you could actually engineer topology disorder to a system. So this was something that people had seen in numerics about a decade before, considering sort of 2D Z2 topological insulators under the presence of disorder. But yeah, you can start with a trivial system, add some random disorder, and actually turn the system topological. So this theory was worked out by Alexander Altman a few years before. The basic crux is that the disorder renormalizes the critical imbalance between tunnelings. And you can see it in the math. This is just some simple third perturbation theory. So this first order contribution actually vanishes because it's random in disorder. And then depending on the sign of this constant, you're either going to sort of flare this up and drive a transition or have it bend down. And it turns out that for off-diagonal disorder, it'll drive the transition as such. And we were able to kind of map this out to a level that we could with our kind of finite system size and see this topological Anderson's insulator. Okay, maybe one other example that I'll touch on briefly is kind of a neat type of, not disordered, but quasi-periodic system and the kind of transport that it admits. This is something we studied with Sridham Ganeshan, Jed-Pixley, and local collaborator Smita Vishweshwara. Thinking about this Aubrey-Andre model, which is a model with a potential term that looks like this. So it's really simple. It has a cosine-like variation shown by this blue line that's incommensurate with the underlying lattice. And this is kind of a favorite of the AMO field because you can make it just by having two lattices that are at incommensurate frequencies. So I did it during grad school, everyone does it. And it also has a lot of really fun mathematical properties. So it's kind of the most constrained, fine-tuned mathematical model where all of my eigenstates undergo a simultaneous transition between being metallic and insulating at the same exact set of parameter values, delta over t equals 2, where delta is sort of the parameter characterizing this potential variation, and t is my tunneling strength. So it turns out that any perturbation you add to this opens up what's called a mobility edge, where I have a different transition point between metal and insulator depending on the energy of my state. So really anything, you look at it weird and it'll get a mobility edge. And so Jed and Sriram cooked up this model that actually had kind of an analytical mobility edge. So this is sort of a different type of parameter variation. It looks like sort of a power law of terms, but it's characterized by this one constant alpha. When alpha is 0, it's the normal Aubrey-Andre. As it gets closer to 1 or -1, it gets highly deformed. This is kind of what it looks like. It's just changing sort of the distribution of site energies at high and low energy. And one can kind of get a really intuitive feel for how it's going to, I have a larger number of states here at low energy. It'll be easier for my low energy states to basically form a metal because there's more states that they can percolate with. That's kind of the intuition I would have. And so, yeah, we were able to explore this and experiment. It was fun. It's the kind of thing that if you did it with real space lattices would be really, really challenging. And it was kind of very simple with the synthetic dimensions approach. And we were able to see sort of shifts of the mobility edge that actually came about due to interactions in the system. So that's something I'll kind of touch on now, which I haven't really highlighted it, but I would say one of maybe the sore points of synthetic dimensions research is that for all the powerful capabilities they've given in terms of engineering artificial gauge fields, there's been this weird conspiracy of nature that has sort of made it such that interactions have mostly been sort of an afterthought in these systems. Things like SUN symmetry and just sort of the weird effect symmetry of scattering lengths for rubidium states and things like that. The interactions have mostly been absent in all the atomic platforms. So in momentum states, we thought that was also going to be the case, but luckily we were wrong. So if I have a BEC and Bose condensed atoms, these are sort of identical bosons, and they're in the same momentum state. And if I have a positive scattering length, I'm going to get some repulsive interaction U. And it turns out that due to bosonic statistics, if they're in different momentum states, I'll actually get twice that interaction. So they'll collide with twice the energy. That's because they have additional exchange energy. So this is great. It means that my interaction energy is not just sort of a constant of motion, but it actually depends on how my particles are distributed in the system, and it can sort of cause things like correlated dynamics. And so this is thanks to Caden, this nice term. I can recast this as an effective local attraction. And it goes like sort of the density squared. And it turns out that you just sort of get for free significant mode-dependent interactions that give you correlated behavior in the system. And I should note there's also were earlier reports from Shimon and his coworkers in June's group on optical lattice clocks. Okay, so what do we? This is work with Chanwei Zhang and Caden. We're just going to start with a really simple system, lattice, and turn on tunneling. And I'm going to do one of two things: either have tunneling be really large, sort of as fast as I can make it, while still being resonant with all my transitions, or make it really small. And what I see if I plot versus the tunneling times is that I either get sort of dispersive spreading, or I can even get all my population just stuck here in my initial state. And if we actually map this out, we see that this is really just seeing a transition that happens when the sort of interaction shift to my local chemical potential exceeds the bandwidth. So when this mean field energy U is larger than 4 times the tunneling, I get what's called a macroscopic quantum self-trapping transition, where everything just gets stuck in place. Okay, so that's nice. It's been seen previously in cold atom systems, but I'd say in a synthetic lattice platform, this was still novel, and it was still kind of the baby steps you need to take to study things like correlated phenomena in these systems. And then after that, following up on some proposal from Chanwei's group, we were able to use this control over phase pretty directly just to drive some Josephson dynamics in the system by creating a two-site superposition, writing a relative phase, and seeing what happens. And so for weak interactions, this is pretty simple, actually. I can think of this as a really silly approximation to momentum state. And so a phase of pi over 2, things fly to the right. A phase of minus pi over 2, they fly to the left. A phase of 0 or pi, they basically spread evenly. And I get these really nice pictures of sort of just wave packets flying around in my lattice. And as I see some nice things, so this sort of follows the first derivative and second derivative of what I expect is the simple cosine band structure of this lattice. Now, as I crank on interactions or decrease tunneling, things change. This gets way skewed. So I get a very skewed current phase relationship. And this changes completely, and I get sort of self-trapping or localization at size of phi and not at others. And we sort of attribute this to something like soliton-like behavior in the system, where I get both sort of self-trapping of my density, but it's still mobile, so it can move like sort of a self-confined wave. Okay, so I'll just maybe say that sort of the next directions for this kind of experiment are to study the quantum aspects of these interactions. So we wrote this earlier as some sort of mean field, classical nonlinearity, but this really is quantum. So if I sort of get some control of my interactions and maybe reduce my number uncertainty in my imaging, I can study things like squeezing. And it actually should obey kind of a one-axis twisting Hamiltonian, where the twisting constant is proportional to the scattering length. And we'd like to use this for sort of proof of principle experiment for quantum metrology. And so the next steps are this new team switching to potassium-39. We hope to have BC really soon, and then to study sort of interaction-driven physics in this system. So I don't know how I am with time. I guess, am I done now?
No, you have some time. I think we go till 3. I mean, we're gonna go through 3 today anyways, but this would be a good place, I think, to let people ask questions. So please type your questions in the Q&A. In the meantime, I have a question here. So I was wondering, things aren't perfectly in the cake. Well, 0 state, and at multiples of this laser frequency, there's some thermal cloud. So can you comment on how much that and the trap and things like that matter in practice?
Yeah, the trap I can probably safely ignore if I do everything quickly. That ignore the motion of the atoms. I think the thermal atoms we mostly ignore, but we have some thermal fraction of order a few percent that probably just leads to some disagreement with some really ideal theory. I would say it's something that gets left around at 0 momentum that we sort of attribute to that state, which is really just not taking part in the experiment. And then there are other things that might happen along the way, like heating, things like that. And for the most part, it's not appreciable compared to the sort of demons we know, the things that we totally expect.
And then there was a question in the Q&A from Sohail Dasgupta asking how many states roughly can be realized in these momentum space synthetic dimensions, and what's the main limiting factor for them?
Yeah, so in 1D, the most we've done in terms of links was 50. And I'd say really the most in terms of sites we kind of coupled is of order 20. The main limitation has to be, it's probably not, but I'd say fundamentally you get separation of these momentum states, in which case the coherent coupling between them turns off if they're separated in space. So we're sort of working in this short time near field approximation, and that it just has to break down at some point. We're soon going to be moving to 2D, where maybe you can access sort of, instead of 20, maybe 400 states, maybe the number is squared on the same timescales. But you probably have to make your cloud big in 2 dimensions. So maybe you want to start with kind of a pancake-shaped trap that's sort of large in 2 dimensions. Yeah, that's about it for the moment.
Great. So there's a question from Chi Space on YouTube asking, what is the symmetry in the synthesized dimension? It seems that the energy is different per site.
Yeah, so it's really yours to define. So by driving all the transitions resonantly, you do actually introduce a flat energy landscape effectively once you sort of do the rotating wave approximation. And the interactions that we have sort of obey that because they're mode conserving. So they're cool with that. But you can turn on an effective potential, and certainly in some of our studies, we've basically used the potential to some effect. Yeah, and I think if you're ingenious enough, you can get something like periodic boundary conditions in that space by kind of opening up pathways in a two-dimensional lattice. So yeah.
Okay, and then maybe one more question before we let you continue. So an anonymous questioner says, how will inelastic scattering at high scattering length affect the amount of time evolution?
Yeah, so it turns out that we're switching potassium-39, and probably one of the main reasons to actually reduce the scattering length compared to rubidium, because in terms of sort of forward collisions to inelastic collisions, you get a win. It's just like sort of detuning your lattice light away from resonance. If you can dump more power in that case, you get a win. Here, at least for mean field effects and certain kinds of things, you get a win by going to smaller scattering lengths. And even for things like squeezing, you should get a win.
Great. So I think that's a good place to let you continue. So.
Okay. So let me just say that it's been a lot of fun working on these momentum state systems, and we think we can push them into kind of a more quantum regime. But we also want to pour over some of these techniques into things that are truly strongly interacting. And for that, we partnered up with Caden and thought about systems we used to work on, like cold molecules, where lots of groups around the world have these really nice pristine systems with sort of localized spins. And one might think to basically add some synthetic dimension to the system and take what is a spin model and turn it into something a bit more flexible and more interesting. So for local relevance, we have a project with Brian DeMarco, led by Garrett and Michael, that we'd like to maybe take in this direction in years to come. But just thinking about it from a theory standpoint, there are many long-lived rotational states of these molecules that interact with each other through dipole-dipole interactions. They're all kind of accessible by microwave radiation in relatively accessible bands. You can get maybe up to a dozen states if I'm just going up in rotational quantum number. And if I'm using different projections as well, I can maybe get many, many more states. And so what this system looks like is that I have sort of microwave-driven hopping and also dipole-dipole interactions that give me some correlated behavior or correlated dynamics between different molecules. And so it's really different than these momentum state lattices. This is really a spin system at heart. I sort of have, if I'm realistic about it, I want to consider kind of one particle per real space site, because molecules do things like react with each other. Rydberg atoms also would be really angry with each other. So it looks like a spin model with some really funky transverse field. And that can maybe be really powerful. So you have the same spectroscopic control as with MSLs. As a selling point, these are global microwaves. So you just kind of, you don't really have to disturb your system to add this in. Most systems probably already have this there, maybe just not with the bandwidth you need to do this. There's a really natural path to strong correlations because you actually start with a spin model and then add on the synthetic dimensions on top of it. And I would say maybe the biggest selling point is that once these systems are realized, they're really going to lead to strongly correlated states that don't have any good analogs in solid state. So I'm going to show one thing that actually kind of does have an analog in solid state. So this is the simplest thing that one could encounter. This is Caden and his postdoc Bhuvanesh had seen this, that for this microwave driving being really strong, you could get basically a free gas of particles where my spin state is uncorrelated between them. If I crank up my dipole-dipole interactions, though, my particles like to form what's called a bound string, or maybe if I'm in a two-dimensional array, a bound membrane. This may be some parallels in terms of quantum magnetism, or if I shrink the synthetic dimension down to two states, I would just call this ferromagnetism, but it really looks a little bit different as I sort of break translation symmetry here, or have this be something like a lattice with no potential terms. And then beyond this, if I add things like gauge fields and closed pathways, I really expect that you're going to get just totally weird physics. And that's both a hard thing and an exciting thing. It's hard because you can't say I'm going to definitely get fractional quantum Hall effect here. These are hardcore bosons and it's not guaranteed, but you're going to get something weird, I guess, and maybe something exciting. And then the cons are that the state detection is more challenging. That maybe one can work around. And then two, just as a practical thing, you don't have textbook knowledge of where all your transitions are going to be. And so you have to go hunting and calibrating. And when combined with this state detection, that maybe is a bit challenging. So Simon Cornish's group has sort of laid the groundwork for doing this with molecules by mapping out the lowest 7 states that one could use. And actually for Rydberg atoms, Tom Killian's group has already just done this. And in talking with Caden, I think this mapping out the lattice is a little bit of a challenge because you don't know exactly where your transitions are going to be, even though ARC is a godsend. And you don't know exactly what the coupling strengths are going to be. So you have to basically calibrate out your Rabi rates for each transition. But with that being said, they're able to do it for single atoms. This is a bulk gas with kind of a micro channel plate detection. And this is a novel probe that I had sort of highlighted. They can do something akin to kind of STM, where they can just change the detuning of one of their Rydberg excitation beams and actually map out something like the edge states here at 0 energy and bulk bands of some Sushri-Verheeger model in these Rydberg lattices. Yeah, so this is really kind of powerful and cool to see. We're hoping to bring this to Rydberg atom arrays. So this is a project led by Jackson and Ganga, developing tweezer arrays for potassium-39, where he really kind of worked really hard combining D1 and D2 cooling to get some great imaging conditions, enhanced loading, and kind of all the steps you would need to get to larger arrays and do Rydberg excitations in the system. So with some nice feedback from Christian Gross's group, who was doing things in a 1064 nanometer tweezers at the same time. Okay, so Jackson has gone to greener pastures. He's the Jonathan Home on working on ions. And yeah, this is the new crew. We've replaced him with 4 people. Hopefully it's enough. And they're going to take up where he left off, building Rydberg synthetic lattices in the system and hopefully studying how dipole-dipole interactions sort of enrich the system. And there's, I guess, probably like 2 minutes left. We can stop for questions, actually. If I don't get to the last part, that's fine.
Okay. Or if you just want to give us if you're promised to make it just 2 minutes, you can do the last part and then people can think about questions while you're doing this.
Here's 2 minutes. These Rydbergs and molecules are sort of the strongly correlated axis of synthetic dimensions. This is on the weird axis. So we're trying to use a very classical system, but with AMO inspired approaches to make totally different Hamiltonians than you can make in a real quantum system. And part of the motivation was basically that, if you're not actually studying quantum correlations or entanglement in a system, so if I'm just studying mean field physics, why go to all the work of using a quantum system? And it turns out that you can basically do everything you would want with something like masses on springs if you're relegating yourself to sort of the regime where the correspondence principle holds and where mean field physics holds. And it has a lot of shared commonalities with neutral atoms. So phonons are neutral. So you have to work hard to get a gauge field for phonons. And it turns out that you can get a whole lot of functionality by actually doing something like measurement and feedback to engineer a Hamiltonian. So this is related to things that people are actually interested in with cold atoms. And around the time that we were getting our results, people were proposing to do this with metamaterials as well. So this is basically it. I guess the main thing I want to say is you're defining your Hamiltonian H by the forces you apply. And this can actually be any Hamiltonian as long as it's in sort of classical limit. So it can have 8-body interactions as long as it's in the classical limit. So it's kind of fun from that standpoint of just making really weird Hamiltonians, weird long-range spin Hamiltonians, things like that. As long as you're okay with not having entanglement. And maybe the last thing I'll show is that with collaborators Tomoki Ozawa and Hannah Price, they proposed that we could use this weird system where you actually can access things like non-Hermiticity to measure the adiabatic Berry phase in a non-Hermitian system, where it actually shows up as sort of population gain and loss. And we were able to make kind of an analog of an Aharonov-Bohm experiment in the system. So here you can go around slowly in parameter space around a PT broken region, which acts as a source of non-Hermitian flux. And you can see, depending on whether you go around clockwise or counterclockwise, you get either gain or loss corresponding to picking up a positive or negative imaginary phase. Okay. And there's the interactions and Josephson physics, and then, yeah. All right, so concluding, yeah, stay tuned for synthetic dimensions. I think they're primed to show some really fun correlated physics in the coming years, and they should be a nice addition to the engineering toolbox.
Great, so thank you, Bryce. That's a clap on behalf of all the attendees. So please submit your questions for our final question session in the Q&A window. I'll ask a mean question while people are typing those in, which is for these classical oscillators, if you're just going to put a computer in and have it control these things anyways, why not take the springs out of the loop and just use the computer to simulate everything? What's, yeah.
So it's actually kind of hard. Okay, on my computer, it's kind of hard. But I'd say we're not actually solving the Hamiltonian as the intermediate step. What we're doing is implementing Hamiltonian. And so you don't need to know the solutions at all to implement the Hamiltonian in the feedback. And so this is maybe going out of reach, but I think this kind of system, although it's super effing slow, can probably do things like, you know, classical icing machines or whatever, you know what I mean? Like those kinds of nonlinear systems where they're purported to have some advantage, or at least be hard to solve. This is a highly nonlinear, non-local system. I think it can do it too. That's not an interest of ours, but yeah.
How many springs do you have?
So in the newest system, 32 is what we're putting in. The old one was 2. You can fine tune better with 2, but yeah. And probably realistically, we would take it up to 100 at most.
So there's a question from Eduardo again asking, in the case where the system localizes and forms a string, how sensitive are these results to the finite size of the arrays?
That's a good question. I guess that's a question for you and Bhuvanesh probably. I think you had considered open boundary conditions, and you saw that in terms of the calculated ground state of the system, it sort of it got there pretty quickly after a few sites. And I guess the nice thing about these dimensions is you really can imagine opening up periodic boundary conditions in this internal space. The interactions might look a little weird in that case, but at least in terms of the connectivity, it can be periodic.
Yeah, that's so. I think it depends a lot on what your tunneling is, but definitely if the tunneling is small, actually, if the tunneling is 0, you get exact results once you go to 3 sites. But as the tunneling increases, you do need more sites. Any other final questions before we wrap up here? Okay, it looks like that's it for today. So thanks again, Bryce. There will be a meeting with Bryce and students and postdocs. So if you are a student or postdoc and you'd like to chat with Bryce, I'm going to put a link just for you in our chat window, and you can follow that and join in. And I also wanted to remind you again, because Thad Walker mentioned this, that the DAMOP invited session abstracts are due, as I said at the beginning, and they're due today. The deadline is today. So don't just submit those, submit them soon. But we do really appreciate when you submit these things. So the link is now in the chat window for the after discussion. Feel free to join at your convenience. So anything else I need to announce? Or should we thank Bryce and finalize? Okay, thanks, Bryce. See you.
All right, thanks, Ken. See you.